So for this, you had a nice overview by Pallavi on the basics of MHD. The theory of the Now let us start going into the numerics. So when you talk about MHD, what is the most fundamental criteria that you can think of in terms of numerics? Any hands up? Wow. Why do you think this is an issue?
Because stable solution.
Stable solution, what do you mean by that?
The error should not grow exponentially. Numerical approximations.
But you said about divergence. So what has divergence got to do with?
So we should be able to look at shock exposure, not
within the equation is not specified for the issue. So the equations can change the direction of the end result.
Right.
Yeah.
To truncation errors, you can introduce magnetic monopoles. We do not want magnetic monopoles in our systems. That is not this. If you do not have any other scheme to correct for the numerical errors that introduce magnetic monopoles, then you will get wrong results. That is the basic premise of what will be discussed. So this is a shortish presentation on a very focused topic. How do you control the divergence of your schemes, of your simulation? So as he correctly pointed out, in the standard set of MHD equations that you're solving, we do not have any constraint on the divergence. We just assume that that is there, but that is not true. The divergence can change. So we need to put additional constraints in additional equations to ensure that the divergence field is maintained. There are other methods as well. In Pluto, there are 3 methods that have been implemented. So let's focus on that. The first is the 8-way. So I will go with increasing order of accuracy and also complexity. This one is less accurate, although it is fine. It is you won't get drastically wrong results if you use that, but it serves a divergence to truncation error, not to machine precision. But it's important to go through how are the steps to the derivation. So in the morning, again saw the flux conservation, right? How the flux is conserved. What you may not often appreciate is there naturally comes a divergence B term when you do this derivation. So I have taken this from last 10 physics. Again, if I go through each and every details and steps of it, take a long. So just write that basic sketch for you to appreciate for the solutions and approximations we have used, which we find that it is naturally true because it comes from the physics background, may not be true from numerics background. Okay, so this is so suppose I have a circular patch like here, and it is moving. So this is the flux or Faraday's law in a moving meat. It is moving from the surface S to the surface S becomes surface S with my d plus dt. What I'm asking is, if this is the flux threading the surface S on C at time t, and this is the flux threading the surface S prime at t plus dt, it is changing flux. And as you have seen from the basic theory of Maxwell's equation, ideal MHD, the flux should be conserved. Okay, so then you do a ddt of this v dot ds at time dt, and then all you have to understand is this is the integral over this entire surface, entire closing surface actually. Sorry, this is integral over this surface. And then how is this magnetically changing? But this is a total derivative because this is a moving, loop. So then you approximate this. You take a delta of the flux. So flux 2 minus flux 1, or flux at S prime minus flux at S, and you get the delta phi here. You divide it by delta phi equals d phi dt. From basic Gauss's theorem, you just get the total conservation of the magnetic. But let's not put it to 0 right now. Let us keep divergence details. So in the Maxwell's equation, we put an extra condition that this is true, but this is just a Gauss's theorem. We transform the volume integral into a surface integral. So these 2 integrals are fine. It's actually simple to understand. And you have to assume some direction of the normal. So this is the outward normal, and for this surface, this is the outward normal. So if my motion is along this direction, I invert it to minus. I hope some of you can understand what this is. Okay, this is a circulation or line integral. Why is it happening? Because it is dl cross dT. Integrate along the line, you get the contribution from the sides. So this is the closed surface. This is nothing so special about it. Then we approximate that at t plus dt, when the contour has reached this level, magnetic field has changed. You do, because the magnetic field is changing to the black as well as anomally is weak. So Taylor expand dt plus del v del t. Put everything here. You will find, and also you have to use this idea that if I'm in the co-moving frame, we don't have any electric fields. So then the total flux actually is zero from Faraday's law. So then you will end up with something like this. If you just go through the steps here, you create the line. Take this over and share the slide with you. So naturally, when you think of this is the standard induction equation. So dv dt is 0, so this will be the induction equation that you learned in 1. But you also end up with this term. Now, in our standard equations of AM physics, we will put this to 0. But for this set of slides, let us keep it 1. So then this term is the source term. So you can actually transform this curl of B cross C with the divergence of this tensor. This is how you write the conservative form of the induction equation in MHD. So del B del T plus divergence of UB minus BU. If you just work out one of this coordinates, you will find this and this are same. But then now you have a source term of divergence B. Good. Now this was slightly non-trivial, so I've sketched the derivation. There is nothing non-trivial in it. You can just work out the algebra. So curl of B cross B, work out the algebra and transform this equation into the conservative frame of the head. You naturally get this term, which means ignore as a standard rule, but not for now. Again, for the energy, you use E cross B cross B. I have worked out I've given the details here, but essentially you have a energy loss term for J dot T, the currents. You use the standard expressions of MHD, E equals to B cross B, the current is this, and current is J curl of B, and you again end up with a source term. So you can see the standard MHD equations naturally permit a monopole source term. It is that the Maxwell's equations do not allow monopoles, that's why you have 0 source term. So this is the standard set of equations, which we call Fowler's method. Now, you might think, why are we doing this in the first place? Let us now look at this equation. So if you just take the evolution equation of the magnetic field and just take a divergence of this equation, you will find that the divergence B actually follow the revolution equation like this. Okay. Now, if you think of this del dot B as a scalar field, by phi is del dot B by rho, then this equation transforms into del dot T rho phi plus divergence of rho u phi. Phi is then nothing but a scalar or tracer field. So yesterday you worked with Kelvin-Helmholtz instabilities. You saw what the tracer field is. Look at the Pluto manual. What is the definition of what is the equation of the tracer field? Tracer field is the thing what field that is being infected with fluid. It sort of marks the distribution of the fluid. So what this essentially means is, if you have divergence inverse, then if you will self-consistently write this equation, if you have non-zero divergence, it will just be affected with the fluid. Okay. Now, if your initial conditions and boundary conditions are such that you do not have divergence, then this will not grow. Okay. So if you are judicious in your choice of setting up the magnetic field distribution and the boundary conditions, then you are okay. Or if you have introduced some errors from somewhere, for example, shocks. Shocks are always problematic when you do not conserve entropy. You can create new source terms, etc. So, for example, you have introduced some divergence error somewhere. It will just be affected carried along as a tracer field without affecting fluid. However, so this is one method of keeping the equations consistent with the fact that there is divergence. But now you can see that your equations are non-conservative. Your momentum energy have a source term. So this is a problem. But this works. This was devised by Powell, and that's what I have in the next slide. Okay. So this was devised by Powell. I can give the reference. So reference is here. The first paper was in '94, then the updated one was in '99. I wanted to show this because just to illustrate what is the Riemann fan or an MHD system like this. So a standard Riemann fan would be 7 waves. Why do you have the standard contact string? Then U plus minus CS, U plus minus the alpine, and U plus minus the negative solutions. If you also include the slope, you can also have one more wave. So this is the 7-wave fan of Riemann. Now, if you put in the divergence criteria, you have another equation. So then you also introduce another characteristic here. So that's why it has 8 waves. That's why it's called Powell's 8-wave method. Just for a comparison, this is the Riemann fan for a 5-wave HLD RMHD. RMHD stands for relativistic limit to harmonize. So 5-wave HLD from the Million in 2009 paper, where you have the left and right fast combination of speeds, the contact discontinuity, and just the alpha speeds. Here we have ignored the other, the CS, U plus minus CS, because it's already encoded inside the first wave. So this is how the Riemann fan looks like in MHD system, just to introduce you to it. Okay, so this is the Powell's 8-wave method, and as I said, this is not very good because if you introduce divergences, the divergence remains in your system. It changes the source terms, it makes the system non-conservative. But if you are good enough and your solutions are stable and steady, and your boundary conditions are okay, you will preserve it. So this is fine. The next method, which is very widely used and quite popular because it's quite easy to implement in terms of the grid structure, etc., is called Generalized Lagrange Multiplier Scheme, GLM, or more popularly called as Divergence scheme. So when you just talk to your colleagues, you just say I have used Divergence scheme, but the technical name for this is GLM. This was proposed by Degna in 2002. And the Pluto implementation is in this paper, Dipanjan and Mukherjee where you can, but essentially physics of it is defined in 2002 Degna. So the basic premise of this is, again, you change the induction equation with another scalar field psi. Okay. So I have taken the equations from the Degna paper. This upward triangle, this is actually the Laplace scale, so del square operator, and this is a gradient operator. So you have a scalar field psi, you add a gradient of psi to it, and for the divergence B equation, you add a linear operator. The form of the linear operator I'll explain in the coming instance. So this operates on psi, and just by manipulating these equations, you can get this. I have actually sketched out how you get this equation. For example, if you just take a divergence of this, the divergence of this is actually the curl. The divergence of this goes away. This is the time derivative of divergence plus the del square psi. Then apply the linear operator on this, you get this. Similarly, the time derivative of this and the Laplacian on 5. So you get this set of equations. You subtract one from the other, you get these two set of equations. Again, let me not go through the details of algebra. You can see, just look at the nature of the equations. So this del T of D, whatever this divergence of B is, and D psi, and divergence B have same evolution equation. So the psi field is mimicking the evolution of the divergence B. So if by your choice of the linear operator, you can control the evolution of the psi such that its value decreases or diminishes, you are also setting that for the divergence B. That is the power of this. Now let us see what we can do for the choice of the psi. The basic and the most easy choice is elliptic direction. It's called elliptic direction because you put T psi equals 0. Let's go back to this equation. T psi equals to 0 means divergence equals 0 by its trivial equation. Now, the way to solve this equation is you first solve the standard MHD equation. The reason I'm explaining this is not Degna Pluto. I'll show what is Degna Pluto. But several codes have different levels of approximation what they've implemented. For example, a variant of this implementation is there in a code called Flash. Okay, so now you first solve the standard set of MHD equations without caring about the divergence. You get a Bn star. Now this may have errors, so you have to correct for it. What you do then is you solve this equation, and you solve a Laplacian or a quasi equation. Sorry, quasi equation. So you get the divergence Bn star minus divergence Bn, and essentially you arrive at it from this equation. So you take a divergence here, and you get a term like this. So then what we'll assume is the starting point of this solution, Bn, not the n star that you obtain after solving the MHD equations. The Bn had no divergence. So Bn can be your initial conditions where you have judiciously set things out so that there are no divergences. Or Bn is a step which has already been corrected in the previous step. So we'll drop this step. Essentially, your Poisson equation looks like this, where your del square psi has to have a source term, which is divergence of Bn star, which is the semi-correct solution that you have obtained, or intermediate solution you have obtained from the MHD. Full Riemann problems or worse, etc. that you have. So now, if you correct this, you use the previous equation and you can find the corrected form of the equation. So this equation. So this is one way to correct it. This is not very ideal because you need to solve a Poisson equation, which is not very trivial. Next choice is d psi is 1 by Cp square psi. Cp is a constant. Let us not discuss what that constant is right now. You can actually look at the guide to see what is the optimal choice for Cp. But for now, it can be a constant going from 0 to infinity. Okay. So if it is actually 0, then you go back to the elliptic corrections. No, so if it's infinity, you go back to the elliptic corrections. Okay, so if this is the choice, then you end up with the equation, evolution equation of psi, which looks like this. This is a diffusion. So what does this do? If you somehow locally generate some divergence, if you spread it out, so the local spike in the divergence is spread out, and also it decays and decreases due to numerical dissipation. So then, also another interesting point of this equation is, if you then go back to the basic equation like this, so put a space square here, and then take a gradient here, you'll find that the psi field is actually not required for you to evolve this set of system of equations. If you just have the divergence, you can just add it as a source term to the induction equation with this Cp square. So this is the parabolic direction, and this is essentially a diffusion. Why I'm saying all this? Because the final direction would be a combination of different things, where it will be diffusing as well as reducing. So then you can have a hyperbolic direction. Why is it hyperbolic? If you have a form like this, L psi del t 1 by Ch square, so Ch is the maximum speed allowed in your local room, but the characteristic speed that you can have.
Sorry, this might be a naive question, but why can't we just like compute divergence and set it?
How would you know
The field distribution to solve the boundary? We can solve it as a.
What you're saying is essentially this direction.
I see.
It's essentially same direction.
Okay.
So locally, you can do that. You can decompose the vector, the magnetic field vector field into a scalar curve.
Yeah.
You take the divergence, then you do away with the curve, and then you again have a quasi equation.
Yeah.
So you have to solve. You can't escape all of that. You have to solve this quasi equation. Okay, so then you have a hyperbolic correction term. If you use this and use the evolution equation that I showed earlier, you will end up with an equation like this. This is a wave equation. Okay, so what is this doing? If you have local errors in the divergence, it is propagating those errors to the domain boundaries at the fastest possible speeds. Okay, so this CH can be chosen such that if you have a time step, you have the CFL criteria, then using that you can devise what kind of the visitor speed that I can have. Whether it be the sound speed or the LFS speed doesn't matter. Just from the time step itself, which you have calculated internally by other arguments, you can calculate that. Fine. So then ultimately what we use is something to decay as well as getting adapted to the domain boundary. So what Pluto does, and this is also not just Pluto, what is also suggested in that and Pluto implements as well, is a mix of the two schemes, the parabolic and the hyperbolic scheme. If you do that, you write out this equation, you will get an equation like this. This is called the telegraph equation. Has anybody heard of it? Telegraph equation? You can also Wikipedia and look it up. So what the telegraph equation does is it transports the local errors in divergence to domain boundaries, but also reduces it. So it has the good of both sides. But so far, all that I was discussing was the fact that I was just playing with potential equation. But I have solved the standard stuff radial MHD equations. So it's just a correction term for the induction equation.
Transport the errors to the boundary. This equation will the dispersion will be exponential or it will be.
It depends on the solution of the telegraph equation. It will be exponential. Not exponential, it will be a path complex solution which can ascend to exponential. Okay, so if you now put this induction equation and the divergence P criteria that you have self-consistently in the MHD set of equations for all the both for the momentum term as well as energy term, you will find that you will end up with some source terms here. So by changing the divergence P in the induction equation, you are making this the system of equation non-constant. So to be completely consistent, Dedner also suggests that we can use something called the EGLM or extended GLM scheme, where the Riemann equivalence universe assumption should consider the source terms. For practical purposes, we do not do this. We only do this when we have extremal situations where the field gradients are very large, because if the field gradients are large, you are naturally prone to react more divergences. If your field gradients are not very large, you can ignore the source terms and just correct for the divergence. If you do not do the source terms, then at least you are conserving the momentum advantage. Okay, so this is the EGLM scheme. Again, EGLM is mentioned. And what are the optimal choice for CP, CH, and all other technical details you can find in the user guide. I'm just mentioning the physics. The last way is called constrained transport. So in this, we have also so far what you've just learned about the numerics of finite volume. We all talked about things existing with volume averages painted onto the cell centers. Now, this scheme actually shifts the magnetic field to the faces. So all the fluid quantities, they are external magnetic fields. They are defined on the cell centers. The magnetic fields are at the faces. So I hope you will back and also see this because it's important for you to follow the figure. So you can see this surface, and this surface. The centers of the surface is where the magnetic field lies. Now, the basic premise of this scheme is you follow this equation. Starting with the basic Maxwell's equation, del B del V curly, you evolve this equation by just doing a line integral surrounding this magnetic field. So for this, you need to know the electric field as the regions surrounding the magnetic. So for this, we also need to evolve or store the value of the electric field. Electric field in ideal English is 3 cross B. It can just be found. But again, note where the electric fields are located. If the magnetic field has to be here and you have to loop like this, the electric fields have to be at the centers of the edges. So electric fields for us, so this configuration is called the staggered field, and if you will do a hands-on today, this talks about. So for a staggered configuration, the magnetic fields are at the faces, the electric fields are at the edges. So edge center and S center. Also for a staggered field, so for example, you are going along the X direction, you can see that the magnetic field of the Bx component has to be at the 2 different places. So in terms of the array structure, for example, if you start off with a 100 cube array for the 3D volume of density, pressure, etc., the Bx will have 101 times 100 times 100. the By will have 100 times 101 plus 100. So just one cell away. Because why? For the extremal cell, you need to have one phase here. And this is another normal component of the reaction. Okay. Fine. So this sounds fine, but there is a problem here. Can somebody find what the problem is? This is related to the electric field. We have computed everything, or the Riemann solvers, etc. Start from the initial conditions being provided at the centers. Then the Riemann solvers are computed at the faces. How do they get to the edges? That is a problem. So this scheme sounds very nice, and by definition, this will just preserve the magnetic field after machine precision. There is no, advection of divergence B errors. There is no, decay of errors. Errors will not even come as long as you have chosen the boundary conditions properly. I'll come to the difficulties of this problem. But the E's are not there. So here lies the approximations that keeping into the scheme. Yes.
Can't we have is it possible to define a staggered grid as an intermediate step to comfort? So there's the grid on which we're solving our MHD equations. The faces are where the Riemann solver is functioning, and then to compute the electric, so the electric field values are also being computed at cell centers. No, at the faces. So defining a staggered grid as an intermediate step.
How would you get the grid for the electric field at the edges?
Yeah.
It's already there. How would you transport the field variables here? How would you come? E is just V plus V, but then you have to transport the E.
The same reconstruction as well.
There is an easier way. You get from the cell fluxes. You get the fluxes at the interfaces. At this points. So during the sweep, the Riemann step, you already can compute the electric fields at the phase centers. I plus half, anywhere plus half is setting it to like half a cell, which is the phase. So during the Riemann step, you can actually get the electric fields at the phases. Now you have to devise a scheme to transport these electric fields from the phase to the edge. There are several schemes to do that. I'm not outlining it. You can do it by just simple averaging. For example, if you have the electric field equation of Bx, you can similarly have it on this cell, this cell, this cell. So just do a 4-cell average. This is what was proposed by Balsara in 1999. For example, you can see that this is, so this H and G are just, references to the electric field components. If you read the paper, you'll understand how he defines it. But these are the electric fields at the phase centers. You can see this is just finding the 4 cells, neighboring to the particular edge, and just doing a simple average. So this kind of techniques are there. There are pros and cons to different kinds of techniques. For example, this is not very physically motivated, just a simple empirical average. There are other better techniques in Pluto, and as you work with them, you get more experience what to use. But you can, for example, use Riemann solutions, etc. But if you get to go to more and more physical techniques, things also start to get a bit difficult to maintain the stability of the solutions. Anyway, so the main problem here is computing the ELFs on the side, and there are approximate schemes to that. So the main technique we use when we start off with the simulation, so advised technique, is start off with constraint transport, because by definition it can preserve the magnetic field very high accuracy. The difficulties with constraint transport is your fields are staggered. Your magnetic fields are no longer at the centers. So it's slightly difficult to work with the arrays, but it's just trivial if you are careful about it. What is more problematic is boundary condition. If you are having this cell at the end of your domain, this part is actually part of the boundary, whereas the cell center is not. It is part of the compute domain. So then, if you are computing this part, actually we do not boundary condition. We evaluate one side just from the diff V criteria. So you find the cell averages at all sides and evaluate that from the divergence V you can find from the one fix. So you use this. This becomes problematic if you have non-standard boundary conditions. Okay, you'll understand this more as you work on it. So I will stop here. Any further questions? Otherwise, we'll go to further.
So with the hyperbolic corrections also, they won't work in periodic boundary conditions. They will.
They will be affected, but they will also be decayed.
Yeah.
As a decay component.
Yeah.
Okay, so maybe we can take the questions later.